So what we're going to do today is we're going to sort of finish this series of lectures on how to collect an EKG. Finally ending up with an actual circuit that will work for an EKG or for any biopotential. So if we're talking about a biopotential instrument, and really thinking about an EKG device. And so, but it could be any biopotential, and so I want you to imagine here and now we have the heart, we have the surface of the body, and as before, we showed that we have two wires that will measure a voltage coming out, and that we will be connecting this to a instrumentation amplifier. So that the output at this stage, if we have a V plus and a V minus, will be V out is equal to some gain times V plus minus V minus. And we discussed last class that as with all instruments, we need to have at the interface with the body some sensors. And in this case, for biopotentials, the sensors are called electrodes. And like all sensors, they will introduce noise. And so, whereas we might, so that what we really have is V out is equal to A times, well, let's say an EKG voltage plus a noise voltage, okay? And we spent some time. And then we said, well, what will hopefully happen is that you can go ahead at this point and use a filter to separate these two things out. We discussed, put it here, that if we look at the EKG in time, and let's say it looks like this, and let's say we have the noise in time, and let's make it a very high frequency noise like this, relative to that. The EKG itself is ultimately composed of different sinusoids, because everything is made out of sinusoids. So we went through a hypothetical where we said, well, let's imagine we have two relatively slow sinusoids. And then I said that this is all here in time. We have time here. And I said we can actually represent both this and this in the frequency domain. But before I do that, the combination of EKG plus noise is going to be the summation of these. So that might look something like the way I've drawn it here. Right? This is really V out. We're getting both of these, right? And once again, we have time. And I explained that we can actually represent this in the frequency domain. And by frequency domain, I mean the sinusoids that you add up to make it. And so in this case, I would say, I would add an axis, and here's frequency. And I didn't specify, but let's say this is frequency 1 and this is frequency 2. I would say in this case that this sinusoid is made out of one sinusoid at F1 and then another sinusoid at F2. this would be, this and this are equivalent. This is the time domain representation. This is the frequency domain representation. And we know they're related because they both relate to this summation of sinusoids. Now, this noise also has a frequency domain representation, which I'll put right here. And again, this axis here is frequency. Bless you. 1, 2, 3, 4, 5. And because this is a higher wiggle, I'm going to put it out here. And we will call this frequency 3, and this is frequency 3. A sinusoid is made out of one sinusoid, and therefore in the frequency domain, it's represented by one chopstick. Right, that's what we discussed. And when you combine these in the time domain, these are added together. Here, we get this in the time domain, but in the frequency domain, this is equivalent to these two sinusoids plus this sinusoid. And so in the frequency domain, we would get 1, 2, 3. We would have an F1, and then I have here an F2, and here's our F3. So this is our F1, our F2, and this is our F3. This thing here is the signal, and this thing here is the noise, right? You can imagine there's like a, there's this sort of, it just turns out that the way I've set up this problem, there's this demarcation between them. And that's what we went through in some detail last time. Looking at this in the time domain, it can be very hard to know what to do. But looking at this in the frequency domain, and these are the same things, right? It becomes a bit clearer what to do. We essentially want a situation where we preserve these sinusoids, and we want to strip away this sinusoid. The circuit that will do this for us is called a low-pass filter, and it's built like this. We have a capacitor, and we have a resistor. And we're going to have a V, let's call it VF for post-filter here. So this is the circuit that we're talking about. Now this circuit, it turns out, also has a frequency domain picture. The picture of this circuit, I'm going to draw it right under here. In frequency, where this now here is gain of the circuit, looks something like, it could look something like this. And you'll notice that there is an associated gain at F1. That's right here. There's an associated gain at F2. That's right here. And there's an associated gain at F3. That's right here. What that means is that this side, and let's, because this is a low-pass filter, I can actually say that this here is 1 and the bottom here is 0. We have all our increments in between. Okay. So this frequency will get a gain of 1, because that's what the circuit does. It puts a gain of 1 when this frequency shows up. This sinusoid here will also get a gain of 1. And this sinusoid will get a gain of 0. And so if we pass this through to the output stage, so this here was V out. If we pass this through to the output stage, Let me put a big box around this so it all goes together. Okay. If we pass this through to the output stage, what is the output? Well, the output is actually VF. All right, I can write that here. This is now VF. This is VF. Well, what we're going to get is this sinusoid will be protected, F1. This sinusoid will be protected, wherever that lands here, F2. But this sinusoid here is gone. And again, all these axes here are in frequency. Okay. So you start with 3 sinusoids, you end up with 2 sinusoids. Yep.
Question about the scaling, frequency 1 and 2 on the frequency
Yes.
at the top and bottom. Shouldn't frequency 2 be smaller than frequency 1?
Oh, you're asking, yeah, so you're asking about the scaling. I'm just drawing it quickly. So you're correct that if the size of these matchsticks should be proportional to the size of the voltage and time. Yes, thank you. And I'm just doing that quickly here, right? Now, this is there for the output, but it's the output in the frequency domain. What does this correspond to in terms of the time domain? Well, if I take this sinusoid and add them together, I get my original signal. So that is why in this case, V sub f in the time domain is now a clean signal, which is what I wanted, right? That's what I wanted to come out of my instrument. I didn't want this to come out of my instrument. I wanted this to come out of my instrument. And a filter achieves this, right? And that, I'm going through this kind of a bit quickly because we went through it very slowly last time, but I want to make sure we're on the same page about that. That's why we need a filter. Now, there may be a situation where we don't need a low pass. We may need a high pass, so we switch the position of the capacitor and the resistor. And there may be some situations where we need other filters, and we could talk about it. But the thing you need to understand now is that we have different filters, and we're thinking about what filters do in terms of this sort of frequency domain representation. Or if you want, a sinusoidal domain representation. And it needs to be emphasized again, this here is a picture of a signal. This is not a picture of a signal. This is a picture of the circuit. It just so happens that they both have frequency here. Here, this means the sinusoids that make this up. This means what this circuit will do to each sinusoid, which we got out of something called sinusoidal steady state analysis. So that's why we did sinusoidal steady state analysis, to give us this picture, okay? And then we can, by lining it up this way, it's very convenient and we can understand what's happening. Okay. In practice, you're probably not going to build, so this is a low pass. Filter. Oh. But I'm going to add now that this is a passive low pass filter. Why is it passive? It doesn't use any active electronics. And as soon as I say this is passive, you're thinking, oh, there must be a non-passive, like an active, right? And that's true, right? I mean, we saw just like with time domain. The only reason we call it time domain is because we have frequency domain, right? If someone's saying there's one thing, there must be something else. In practice, you will probably rarely use passive low-pass filters because the active low-pass filter is not that much harder to make and is going to be much more useful to you. And so we need to describe now that you understand, generally speaking, why you might use a low pass or why you might use a high pass, right? I need to describe why you why you would do this in the active stage. But let me illustrate that right away, right here. Let's say in this situation, you want to do some low passing, and you want to do some high passing. Right? What I mean by that is you want to remove high frequency noise, and you also want to remove some low frequency noise. I want to make that clear. So this was the frequency domain. And we go back here to our F1 and F2. I now am going to put here FA and an FB, where the high frequency noise is the FA, and the low frequency noise is the F sub B. So what we want to do here is we want to trim from the high and from the, so we can't just use a high pass, we can't just use a low pass, but in fact you can use a high pass and then a low pass. And this is not maybe, 100%, everybody, just so you know right now, every biopotential signal will require both. So you might say, well, this is what I'm going to do. I'm going to add another stage here. I'm going to say, well, I'm going to add another circuit here. And this time, I'm going to do it this way. And here maybe I have my C sub 2, and here I have my R sub 2. And so what do I have here is I have two stages, right? I have my low pass stage. And here, I have my high pass stage. But there's a problem here. You can't just stick things together. We talked before when we talked about like voltage dividers, you can't take a voltage divider and then stick another voltage divider and think it's going to work like one voltage divider followed by another voltage divider. These things will start to interact with one another. So now you have a new circuit. This circuit has a resistor, a capacitor, another capacitor, and another resistor. And if you want to know what this circuit does, you need to resolve this using sinusoidal steady-state analysis. Now, I'm not saying this won't necessarily be useful for you, but what I'm telling you is it's not going to be the same as this plus this. It's going to be something else, right? So right away, that's an issue with using passive that won't come up with active, and there's going to be other issues as well. So it's just going to be easy, even though it takes a little bit more introduction now as we introduce active filters. Once you know how to use them, they're going to be used in everything, everything. So let's talk about active. So now we're going to talk about active filters. And I'm going to introduce active filters at a high level so that you understand it. In reality, you're only going to need a high pass and a low pass active filter. I could just give them to you, but I want to make sure you understand where it's coming from. And then you can also get into something called a band pass filter, which ends up being very useful. Let's start with an active filter. So an active filter means that we have here our op amp. And let me draw it the other way.
Professor?
Yes. Yes.
I was watching one of the videos you sent, and
Yes.
it had a low-pass filter with an inductor. Is there any reason why, I guess, is it less important than the one that you showed us? Or?
Right. So the question is about making filters with inductors. So we have not done inductors. We will get to inductors in this class. And we'll show how to use them as sensors. They tend not to be used as circuit components. And one reason for that is when I build a, let's say I built a circuit like this. I don't want this capacitor to somehow talk to this capacitor via this gap here. Or another way to think about it, let's add another circuit here, like another capacitor here. I don't know, I had some other circuit here, right? Unrelated. You certainly don't want this circuit talking to this circuit, right? I mean, you put them on different breadboards. The problem is that once you start adding inductors, you get into concerns like that. Inductors can communicate at a distance. In fact, it's what inductors are often used for. And so for that reason, we are very hesitant to build circuits out of inductors, because now all of a sudden you have to be like, is there anything near it? And stuff like that. So we will talk about inductors, but that's why you don't see them. So generally speaking, if you're building a passive filter or an active filter, you have to have a very good reason to use an inductor. I don't know what that reason would be, okay? And we'll see, and when we get to inductors, that will become clear. Okay, so let's do active filters. So let's start with this one. I want to start with a, we have our V in. Let's do this. Okay. Yeah. Okay. This is not something you're probably going to make, and I'll show you why. But it's a great introduction to active filters. Right? Let's think about it first as a circuits problem. All right? We have our V in, we have our V out, and we want to understand what this circuit does. The approach that we can use is the approach that I've gone through so far, around sinusoidal steady-state analysis, right? So we can apply sinusoidal steady-state analysis to solve this circuit. Sinusoidal steady-state analysis tells us what happens when V in is a sinusoid. However, as I hope you're starting to appreciate, it ends up being very useful in general, right? Once we know what a circuit does to sinusoids, we often have everything we need to know. And the question, of course, is what is V out? And if sinusoidal steady-state analysis works, V out is just going to be B cosine of WT. That's if it works, of course, right? For sinusoidal steady-state analysis, the only thing we need to know is given an A, what B comes out, or another way to say that is we have a gain, maybe we'll call that C, and that's equal to B divided by A. So just to frame the problem, that's sort of always what we're thinking about. Okay. Now, this might give you pause. Now, we've talked about how to deal with this is now a basic op-amp, not an instrumentation amplifier, right? This is an op-amp. We've talked about how to deal with op-amps. And I gave you, in fact, 2 rules of op-amp. Okay. We also talked about how to deal with capacitors. And I gave you 2 rules of capacitor. And of course, after my rules are other things, but those other things just tend to be Ohm's law, right? But now you have both an op-amp and the capacitor, right? Here's the good news. You already know everything you need to know. I don't need to introduce any new rules for you, any new principles. I'm going to show you how you can just go through exactly what you know and get the answer. Okay? Good news. All right? Let's see how it works. The first thing we're going to do is we're going to get rid of this capacitor. Okay? Or specifically what we're going to do is we're going to convert the capacitor to a 1 over JWC. Now this is part of this sort of, that's rule number 1, because rule number 2 tells you that you can now treat this as a resistor, right? That was, right? You can go back and watch those videos, and I spent a bit of time on that. Okay, so what I'm going to do here is I'm going to cross this out. I'll put a box around this to remind me that this is now a resistor, which has a value of 1 over JWC. Yes, the value of this resistor is imaginary. Yes, it's a function of, if this is 7, I have to put 7 here, but it's a number, to be clear, right? If capacitance is 1 and this is 7, and this is 1 over J 7, it's a number. At this point, we're done with that aspect of it, right? We now just have a system here with one resistor with this value and another resistor with this value. What's the name of that circuit? Do you remember? So the input's coming in on the negative inverting end, so we call this a amplifier. I set you up for that, okay? It's just an inverting amplifier. When you have a resistor and a resistor connected in this way, it's just an inverting amplifier. Well, when you have an inverting amplifier, we know that V out is equal to minus RB over RA. We already know the answer, right? Because we derived it earlier, right? That's the equation for an inverting amplifier. And if you want, I'm going to do this. I'm going to put a square around this, and I'm going to put a square around that to remind you that these are the elements. And so I can put a square around this, and I can put a square around that, okay? This value here plugs into here, and this value plugs into here. You need to realize it's the same thing. This resistor just has this weird value. And so we can plug in directly. Right? So what I'm going to do is two things. I'm going to plug in directly, and then I'll derive it as if I couldn't plug it directly, just to convince you that it's true. If I plug in directly, I will therefore say here that V out is equal to minus, so I'm going to get 1 over J WC over R is equal to minus 1 over J WC R times Vn. Times Vn. And this thing here is the transfer function. This is the circuit. Every circuit has a transfer function, and this also has a picture that we'll draw to, okay? But I want to show you that if you didn't know that, or you didn't recognize that that's what you were looking at, you could still figure it out. And the way you would do that is now by applying the two rules, right? These were the rules of op-amp. Let's apply my two rules of operational amplifiers. Rule number 1 sets the, call it current inputs to 0. And what we mean by that is that this current here is 0, and this current here is 0. All right, that's that 0. And then rule number 2 of op-amps, when you have negative feedback, and they always have negative feedback unless it's the comparator, okay, unless it's the comparator. Rule number 2, when you have negative feedback, is that V plus is equal to V minus. And once you apply these rules, you can ignore the op-amp. Oh, okay. So the capacitor is now a resistor, and the op-amp is now gone. The op-amp is now gone. We just have a resistor and a capacitor in series. That's all. And once you've exhausted my rules for capacitors and for op-amps, right, you're just left with Ohm's law. So now you just start hammering away with Ohm's law. Now at this point, it may not necessarily be clear where you should write Ohm's law first. But it turns out you can't really go wrong. If you just write it enough times, you will get the answer. But remember, we're trying to figure out what V out is. So this is what I'm going to do. I'm going to write Ohm's law twice. I'm going to write it for this current, and I'm going to write it for this current. Let's call this current 1. We'll call this current 2. Okay. What's Ohm's law for current 1? Ohm's law for current 1 is going to be this voltage minus this voltage divided by this resistance. So that's going to be V in minus V minus the negative terminal over R. Now, V minus is equal to V plus, and V plus is equal to 0. Right? I'm going through this a little bit quickly, but again, we did this for already. We did exactly this for the inverting amplifier, and so therefore this is equal to V in over R. Great. I sub 2. All right, now we've got to be careful. I sub 2 is pointed this way, so it's going to be this voltage minus this voltage divided by this resistance. Can I do that? Yes, because I can treat this as a resistance, right? So we're going to get V minus minus V out over 1 over JWC. This is a resistance that's being plugged in to Ohm's law. And I want you to get used to that, right? I'm just plugging in a number. It's just a number. But I know that V minus is 0, because V minus is equal to V plus is equal to 0. So therefore, this is simply going to become minus V out over 1 over JWC. Now, we then go back and apply, because these currents are 0, we know that these taxi cabs have to all go like this. So therefore, I1 equals I2. That means that I can put little equal signs on this end as well. This is equal to that, right? And so what can we do? We can take, to get it to that form, we're just going to take this 1 over JWC, and we're going to track it on over here, right? We can multiply both sides by 1 over JWC. And that's this. Now I knew it would work out because it had to work out, because I already solved inverting amplifier. The fact that this resistor happened to have this odd thing doesn't change the fact that this was what had to come out. This was what comes out when you have an inverting amplifier. I just showed you how to do it straight through. And so any circuit I give you with resistors and capacitors and amplifiers, doesn't matter how many resistors, how many capacitors, and how many op amps, you can get the transfer function using only these basic rules and basic algebra. Sounds good? Okay. Now, we're not done, because we have this pesky J, right? And J is imaginary. We live in the real world, okay? And I don't know what quite to do. I mean, I could take this and plug it into here, but I would still have an output in terms of the J, and I need the output in terms of a real number. So there is an additional step, which we talked about, which is you now need to take this transfer function, which is in the form A plus BJ, and convert it to a C. Right? That's what I told you needed to do. Now, in all fairness, a lot of these steps that I'm telling you about, I never justified them to you. And maybe we'll get to that in another class where I can go through all the derivation that justifies all these steps. What I'm telling you just right now is that this works. So, okay, it works. So we have to take this and convert it to this. right? How do we do that? Well, if we look at this term here, let me write it. I'm going to go here. We have minus 1 over JWCR. Now what I'm going to do is, remember we always get these J's in the denominator and we don't like it in the denominator. In this case, you'll see it's not even a problem. I'm going to multiply this by J over J. And I'm going to get minus J over, and then the J times this J gives me a negative, right? A negative. And that negative is actually going to cancel this negative. Turns out it won't matter, but anyways, it'll be J, W, C, R, right? Or if you want to write it even more explicitly, this is going to be 0 plus J times 1 over WCR. I wrote it this way just so you can see it, that it's in this form, right? If it wasn't already obvious, right, that once we have this, we have no A, there's no real component, and we have an imaginary component that's 1 over WCR. And to convert this to get to C, we have to use this equation here, but we're just going to get the same thing back because C now is going to equal to the square root of 0 squared plus 1 over WCR squared, but again, it's just going to come right back out, WCR, right? Because you can just see that we're just going to get back what we started with. C is just equal to B in this case, and if this had been negative, this would have been positive anyways. That's why I wasn't worried about it. Okay, so now we have our answer. Now we can say that we'll do it right here. That we can go to V out is equal to 1 over WCR times V in, which means that V out is equal to 1 over WCR times a cosine of WT. That's the output. And I want you to remember these are just numbers, right? So this could have been 7, 3, 2, 6, 3, right? These are just numbers that we wrote out in this term. We could have gone through this whole derivation with actual numbers. And that's the answer. And this here, right, is the transfer function. I'm going to plot it now. Let's plot what this looks like. Specifically the transfer function here. I want to see what the transfer function looks like if we were to plot it. You could say, but wait, why aren't you plotting the whole thing? Well, the transfer function is the thing that you multiply the input by to get the output by. The transfer function is the equation for the circuit. It does not consider the input or the output, right? That's the transfer function. So this is our transfer function. So here we have, let's say, our C, and here we have our frequency, W. And irrespective of what C and R will do, you can see that as W gets big, this will be small, but as W gets smaller and smaller, this will blow up. For smaller and smaller W's, the gain starts to increase more and more. Oh, is the door closed already there, or you want to close it? Yeah. Right. Okay. what I want you to understand is that this picture and this circuit are the same thing. This is the picture of the circuit. This is the circuit of the picture. If you want to know what the circuit does, look at the picture, right? This circuit here does not like high frequencies. And it really, really likes low frequencies, okay? And it has a name. It's actually called an integrator. Now, I know you've heard about integration before, right? But this circuit here is called an integrator. We actually don't use it. I don't think we would use it. I don't think we would use it, okay? We don't use it because you can see at low frequencies, it kind of blows up a little bit, and that ends up being problematic. So this circuit you will not use. I'm going to show you one more circuit you will not use, and then I will show you the circuits that you will use. All right, but there's a buildup here, okay? What's the point of showing you circuits if you don't use them? Because when I get to the actual circuit you're going to use, it's going to be 10% more complicated than this. And so when I introduce that 10% more complication, I just want you to be, I want you to be able to capture that without difficulty. So that's why, yeah, if that makes sense. Also, it's not a bad thing. But yeah, you'll see. Sort of, I try to show you things in a way that feels so repetitive, it's almost boring. And so that by the time you're getting the concepts you need to know, it's really easy to grasp them. Maybe that's another way to think about it. Here's another circuit. I'm going to, I'm just going to erase it. And this one we'll do quicker. It is another amplifier, and now I'm going to put the capacitor here. Okay. We only need this much space to solve it because you know what to do. The first thing we're going to do is we're going to replace this capacitor with a 1 over JWC. And now we can treat this capacitor like a resistor. So we now have a situation where we have a resistor and a resistor. Right? This is, I showed the other, before we had the capacitor here, right? I didn't draw the same thing again, right? The capacitor is here, right? So, huh? It's different, thank you. Okay. I could go through this derivation again, but don't you already know that when you have a resistor and a resistor, this is the answer? The fact that RA is this value doesn't change what RA is. So I can in one step say that V out is equal to negative this resistor, which is R, over this resistor, which is 1 over JWC, which is equal to minus JWRC. Wow, right? You had this complicated thing, op amp, resistor, capacitor, boom, one step. That's why we do things slowly, right? You can imagine if I'd started here, you would, that's why, yeah, you get it, okay? Now it's obvious, right? Now it's obvious what's happening here. And this is times, this would be times Vn, and this would also be times Vn. And I'm particularly interested in this thing here, this transfer function, the same thing I drawn here, right? Since that relates the input to the output. Let's draw that transfer function. Let me draw it. I'm going to draw it in purple over here. Now you can see that when the frequency is very low, the gain is very low, but when the frequency starts to increase, it goes up and up, right? The higher the frequency, well, the bigger the output. It has a nice symmetry against this one, doesn't it? This circuit really likes high frequencies. It doesn't like low frequencies. And it's called the differentiator, because differentials like high frequencies. Okay, you will also not use it, so we will move on. But what you got now is you see that, oh, you got this, right? You see that? You got it, right? So now let's do one you're actually going to use. One of the most useful circuits you're going to get, since I've gotten complaints about not useful circuits. And this one, do it like this. We're going to have our Vn. I'm going to call this C. I'm going to call this R1. And I'm going to call this R sub 2. I'll give this a name. The active high pass. This is the high pass you're going to make, or versions of it. Okay, now, maybe at the start of this lecture, you would have been like, whoa, there's a lot going on here. But maybe now, because we've gone through these simpler circuits, right, you will be able to do this relatively quickly. Let's try. Well, these are the rules, right? Let's start. Let's go through them. 1, take this capacitor and replace it with another element, another resistive element that we're going to call 1 over JWC. And now we're done. And now we're going to go ahead and apply these rules as well, right? But when you have two resistors in series, we can, of course, combine them into a single resistor, right, from the perspective of Ohm's law, which is equal to RA plus R sub B. These are two resistors in series. It's not a resistor, but I just said you can use it, you can treat it like a resistor. That's the whole point of the exercise, is that you can pretend like this is a resistor with the value 1 over JWC. It's remarkable that you can do that, but you can do that. And so therefore, I can rewrite this. I'm going to redraw it just so it's super clear. I have a Vn. I have a new, I'm going to put a resistor here. Like, let's see if I can draw it in. Go like this. R sub 2. And in this block, I have a resistor which has the value 1 over JWC plus R sub 1. There is a single resistor, hope that's clear, right? There's a resistor here that has this value. It is a number, it's a complex number, but it's a number. And there's another resistor here. Well, this one hasn't gone anywhere, right? It's the same old resistor. And that's it. Okay, so now what we have is we have an op amp, negative feedback. There's one resistor here, and there's another resistor here. It's this. It's just this again. You can say, is it always going to be that? Yeah, like I love this class is so full of repetitions. It's always that. It's always this. It's always this. So the only thing we have to do to figure out the transfer function is put this resistance over this resistance. And we're done. And so we can say, should I combine this? yeah, maybe it'll be easier. This here is going to be the same as J, W, C, R sub 1 plus 1 over J, W, C. Do you see that, right? Because this is R sub 1 JWC over J, yes? And by see that, I also mean let me know if I made a mistake, right? This is this, I'm going to put a square around it to remind you that this is a single resistor, which has this value. And notice how this C and this R sub 1 found each other. Maybe I made that joke like there's two people in the party who always seem to find each other. The R's and the C's always find each other. It's amazing. Here they are, right? Who's this one going to get married to? Let's see, right? Because this one still needs somebody, right? Okay, now we're ready to write the equation, which is that equation right here. I'm going to say V out is equal to negative of this resistor, so that's going to be R sub 2, over this resistor, so that's going to be J, W, C, R sub 1 plus 1 over J, W, C equal to minus J, W, C, R sub 2, there they go, right? Plus J, W, C, R sub 1, plus 1. Did I do it right? Hopefully. Okay. Oh, I always forget. This is times V in, and so this is also going to be times V in. And just like that, we have our transfer function. Which, if you don't like fancy words, is the thing you multiply the input by to get the output. Okay? So I'm going back, so now I want to go back to that critique of why I'm showing you circuits. I like that critique. Why am I showing you circuits that you didn't know? Because if I had started with this, I think it would have been a little bit confusing, but by starting with the other ones, now I see what you're doing. You're just taking that. Make sense? Yeah. Okay. Why is this circuit so useful? I think to understand why it's useful, we are going to need to get rid of some of these J's, right? And convert it, right, into another form. I'm going to do that with specific values, because oftentimes we go through keeping it as J's and R's. I want to go through now and use a specific value case that you could track it through without it. I just want to say, let's go through a specific example. I want to say that the capacitance is, I'm going to make it easy. 1, R sub 2 is 2, R sub 1 is 2 also, and the frequency, which I do need to know because that's going to factor it in, right? The frequency of the sinusoid arriving in is 0.5. All right, so I'm assigning values to this capacitor, to this resistor, and to the frequency that showed up. So these are the values that I can now plug into here. So now we're talking about a specific case. So I'm going to get negative J times, let's see, 0.5 times 1 is 0.5 times this is just 1. I mean, I picked it, right, to make it easy for myself, but it's all going to simple. I mean, it could have been 3. And here I'm going to get J times 0.5 times 1 times 2, also 1, because I picked it. okay, to be easy. So I'm just going to have j times 1 plus 1. So let's continue working with that. I'll stick to blue. We'll move here. And so there, and times Vn. Now let me just rewrite the transfer function as minus j over j plus 1. All right, I'm just picking up by that. Now, we have a way to get this, we have a standard way to get this into that a plus bj form. So I'm just going to multiply this times 1 minus j over 1 minus j, because this is going to be the complex conjugate. All right? And so we're going to get minus, I have to do this right, minus j times 1 is minus j. And then minus j times minus j is going to be plus 1. I did that right. All over, it's going to be 1 squared plus j squared. Is that right? 1 squared plus j squared is 1 minus 1. Huh? What's that? Oh, j times minus j squared. So just, it'll give me a 1. Sorry, 1 plus 1. The 1 squared, I get a minus j squared, and then the intermediate terms cancel each other out. Huh, okay. And so that's just going to be minus j over 2. And so now I can write this out in terms of this a plus bj form to make it explicit. So that's going to be, I'm going to go right here. I'm going to write this as 1 half plus a minus 1 half j. All right? A plus bj, right? Let me know if you see any mistakes, okay? And now I'm going to convert this to the c term, right? Where the c is going to equal to the square root of 1 squared, half squared, plus minus half squared. So I'll just say minus half squared. So 1/4 plus 1/4 is 1/2, right? Square root of 1/2. So c is equal to 1 over the square root of 2. And we have seen that before. Okay, so what this means is, for this specific example, to be very clear, we had a situation where the input was we didn't specify what a was, cosine of 0.5 t, right? This was the V in, and the V out is going to equal this number here, 1 over the square root of 2 times a cosine of 0.5 t. So the input came in, and the output came out, and it was a little bit smaller than what had come in, right, as I'd picked the numbers. What does this function look like in general? I mean, I think that's interesting, but let's look at what this function looks like in general. I want to plot here the gain, the C, over different possible frequencies, right? The frequency W. And I can do that in part, all right, by inspection of this term. Let's say, for example, and we've done this before, right? Before we started to break this down, right? Before we came up with a way to break this into the C term, we would look at these terms directly and interpret what they do, and we would do that by looking at extremes. So let's look at the extremes. Let's say we talk about the situation where the frequency is very big. So that's all the way out here. Okay. So we have this term here with a very big W ends up being much bigger than this term here, right? So if this is a billion, this one, we don't really need to worry about it, right? And so I can say that for very large frequencies, this C is approximately minus J W C R sub 2 over J W C R sub 2 R sub 1, right? This is for very high frequency. This cancels, that cancels. And we're left with only minus R sub 2 over R sub 1. Minus R sub 2 over R sub 1. This is the equation we would expect if this capacitor wasn't here, right? If the capacitor wasn't here, it should be minus R sub 2 R sub 1. Where'd the capacitor go? Well, when you have big frequencies, this number becomes very small, right? This is a very small number. Capacitors are not players at low frequencies, at high frequencies. At high frequencies, capacitors become like lines. If we have a very low resistance, like 0, and we add it to another resistance, the total resistance is just this one. You see it here too, right? Look, put into something, if you put a very high number and a very high number here, right? Once again, the R1 will pop out. You can see it anywhere, or here, this is small and this, right? So at high frequencies, it's interesting, this capacitor is kind of, I'm not involved. And that's always true for capacitors, okay? At very high frequencies, they drop out. And so here, at a very high frequency, I'm going to just, for my own convenience, I'm going to call this negative here. So I can just write R sub 2 over R sub 1. Okay. What about at very low frequencies, right? So now we ask the question, what if the frequency is very low? Well, that means that this W is approaching 0. So here we have about 0 times a bunch of numbers, right? And that's going to give us a low number. Yes, an imaginary number, but a very small number, right? And down here, what we're going to have is J times about 0 times plus 1, right? So this reduces to, in this situation here, C is approximately equal to, I'm going to say minus 0 over 0 plus 1, which is, 0. And so that means that we are here. And in fact, if you go across all the frequencies, you will find that there is a transition point, right? This here, we like to call the cutoff frequency, right? It's the difference between when things are about 0 and when things are not 0. And this cutoff frequency is going, and the cutoff frequency, right? We know at the cutoff frequency, the gain is 1 over, well, for this thing, it was 1 over square root of 2. But in this case, it's going to be 1 over square root of 2 of R2 over R1. It's sort of like we're starting the transition, but we're not quite there. We're like at 67% of it. This is the picture that you will get out of this. This is the picture of this circuit. And the cutoff is at 1 over R, I want to say it's going to be R sub 1C. Hope I didn't get this wrong. Hopefully I didn't get that wrong. Because there's 2 resistors, okay? But I believe it's going to be at WC is 1 over, so that's going to be the cutoff in radial frequency, right, or 1 over 2 pi. All right, there's a lot going on here. This is a high pass. We've seen this before. It's this one. When we did this circuit, right, and we figured everything out, we had the same picture. There's one interesting difference, however. When we did that circuit, this peaked at 1. But this one doesn't peak at 1. This one peaks at R2 over R1. Now, if R2 was 1 ohm and R1 was 1 ohm, we're back to 1. But if R2 was 10 ohms and R1 was 1 ohm, this would be at 10. Right? If we picked R sub 2 equals to 10 ohms and R sub 1 equals to 1 ohm, then the gain at these very high frequencies is 10. So we actually have a situation where we can not only do a filter, but we can also do an amplification. It's a 2-in-1. And if you are lazy, 2-in-1s are nice. Right? Why would you do an amplifier and then a filter? In this case, you get them together. Right? What do you have to pick? You have to pick 2 resistors and 1 capacitor. The resistors are going to set up your peak gain, and then the capacitor will dial in where the cutoff is. And this is an active high pass. It is a preferred circuit to use. This is the circuit you're going to build. Let me show you the other one. And this is your active low pass. Let's think about what it does. Let's think about what it does. We're going to replace this capacitor with the 1 over JWC, right? So this is going to become 1 over CJW or JWC, right? That's what it would be the term here. At this point, right, we just have a bunch of resistors, right? But these 2 resistors are in fact in parallel, right? So we have drawn it here. We have 2 resistors in parallel, R sub A and R sub B. And then from perspective of Ohm's law, what's the equation to combine these 2? Do you remember? RA times RB over RA plus RB. Okay? This is going to be, from an Ohm's law perspective, the same as this. You notice that one thing I want you to notice about this is, if either one of these is small, the combo is small, right? If this is like 0 and that's 1,000,000, we still end up with 0, right? For parallel to work, right? For like, it's like two people pushing something, I don't know, they both got to be strong. If either one is weak, then the whole resistance collapses. Okay. So now what we're going to do is we're going to replace this with another resistor, right, which is a single resistor which has these values. So what we're going to say is we're going to say R sub A times 1 over JWC over R sub A plus 1 over JWC. Right? This is a single resistance value that is this resistance value. And we can simplify this a little bit by multiplying both top and bottom by JWC. And so we're going to be left with R sub A over R sub A, well, JWC plus 1. Wow, simplified a lot. And look how this resistor, wait, no. No. Yeah. Right, you saw how this resistor found this capacitor. This is this chunk here. So far, so good? So now we have a resistor here of this value and another resistor here of this value. We're right back here again, because we always will come back here, because it's all these circuits with these different sort of negative loops, they always collapse. They always collapse to this. And so we can now write in a single step that, that V out is going to equal the negative of this side. Well, that's this negative here, right? So I'm going to say, well, we'll just put a negative here. R sub A over JWC R sub A plus 1 over this one, R sub B. Or if you prefer, minus R sub A over R sub B times over R sub B times 1 over JWC R sub A plus 1. Little crowded, but there you go. If I didn't make any mistakes, here you have your other transfer function. So I left that there. Of your active low pass. And this here was our active high pass. Right. These are our two sister circuits. We can look at this and we can already start to figure out what is happening. Let me draw it. I'll just try it here. Okay. Without even decomposing this, let's look at what's happening here. If the frequency is very big, we get 1 over j billion plus 1, right? 1 over a billion. This term here becomes very, very small. And in fact, it will crush this term as well. So for high frequencies, we are here. Right, we're at 0. For low frequencies, this term starts to approach 0. Right? We see that 0 here? So j, 0, 0, 0. Okay, 0 plus 1 is 1. And 1 divided by 1 is 1. And so we're just left with RA over RB. Right? And so here, and just for my convenience, I'm going to call this the negative C again. And I'm going to say that up here, we have at low frequencies a point, and that point is RA over RB. And then there's going to be a transition. And this, it's not going on here. Well, anyways, this is the picture of this circuit, right? Every circuit has a picture, and the picture is the circuit, and the circuit is the picture. And this is, of course, a low pass, which is what you were promised. Low pass, high pass. And this looks a lot like the low pass that we did here, except here the gain could only go up to 1, but here it can go up to RA over RB. RA over RB. Okay. Now let me show you a trick. It's a good trick. This is a trick where if you look at any circuit that looks like this, you can just immediately know what's going to happen. Okay, without doing anything. This is what you do. You look at a circuit that has a capacitor in it. We don't need this anymore. We don't need this. Let's go back. You're just back to the capacitor. We don't know how to do sinusoidal steady state analysis. This is what you do. You imagine two situations. The first situation, right, but here's the trick, is when the frequency is very high. And what you do is you take all the capacitors and you turn them essentially into a short, a wire. And you can imagine that when the frequency is very low, you take the capacitors and you turn them into a very large resistance, almost an open circuit. And if you do that, you're going to get the answer. Oh, Professor, why didn't you tell us all along? Well, you still got to know the middle part, right? Watch. Let's go to this one here. First situation, when the frequency is low, replace this with a short. So there's a wire here, right? A wire means it's not here, right? So what does it look like? What is this? What's left? What's the name of the circuit? Inverting amplifier. What's the equation for the inverting amplifier? R2 over R1. So you know what the circuit does for high frequencies. It's just R2 over R1. Okay. For very low frequencies, you replace this with a very large resistor, like a billion, right? So what you have now is a billion plus R1 over R2. A billion plus R1 is like a billion, right? So we have a billion, a resistor here that's a billion, and we have R1. R1 over a billion is 0. So that means that this circuit at low frequencies will have a gain of 0. See, and that's it. And then in between, you just draw a line. Let's do this one. High frequencies. Replace this with a short. Well, remember what I was emphasizing with the two resistors in series, right? If either one is weak, they're both weak, right? That's how parallel works. So if I have a short and I have an R2, this whole thing is a very small number. Very small number, an RB. Very small number, it's an RB. You see? So right away you see that this circuit here will have a gain, right, of about 0 at high frequency. What about low frequency? Well, at low frequency, we replace this capacitor with a massive resistance. If you have a massive resistance in parallel with R sub A, the result is actually just R sub A. I should have left the circuit up, okay? But a billion in parallel with RA is just RA. You can look at the equation for, right? So that means that when at very low frequencies, I have this. What is this? It's an inverting amplifier. What's the gain of this inverting amplifier? It's RA over RB. So that's the trick. Does it always work? As far as I know, it always works. And it will give you it will right away tell you what the circuit does. Is that enough for our purposes? It's not enough for our purposes because we have to know where the cutoff lands, right? So we need to know another bit of information, all right? And the cutoff is in this case, 1 over R sub AC. Isn't it weird? All these cutoffs are always 1 over RC, 1 over RC, 1 over RC, right? They're always 1 over RC. Now, when you have these kind of circuits, you need to be a little bit careful which R are you talking about, right? Which R got married to the C for the perspective of the cutoff, right? But it's always 1 over RC, so repetitive. And in real frequency terms, we talked about last time, 1 over 2 pi RC, okay? Now here's the nice thing about active filters. I'm going to try to draw it. We couldn't do this. But what you can do is you can take this and insert it here. I'm not going to redraw the whole thing. This is your active high pass. And you can put after that your active low pass. And then you'll get your V, whatever it is, VG for V good. What does that mean? If you wanted to imagine it, I could take this line here. Let's do it. Take this line here. Which should we do first? High pass. And run it here. And take this line here and run it here. Connecting these circuits in this way does not impact that input. You can daisy chain a whole bunch of active filters because the information basically is only going to flow this way. You are allowed to do that with, in general, you are allowed to do that with most of these active filter designs. So whereas before I said you could not, now you can. And when you do that, the result will be a net transfer function that looks like this. Where here you have your frequency, and here you have your gain. And you, in fact, have 2 cutoffs. I know it's getting messy here, okay, but get the idea. There's 2 cutoffs. Let's call this WC high, and therefore this was WC low. And so here we have our WC low and our WC high. That's where they come from. All right? So now you can design, and that's going to be, I'll give you your homework now. That's going to be your homework to design. I just want to note one thing. It's a little bit confusing. The high cutoff comes from the low pass filter, and the low cutoff comes from the high pass filter. See, there's a little bit of a switcheroo. So be careful. Yes.
So let's say we switch the active high pass with the active low pass, will the graph be the same?
No, exactly. The order doesn't matter. In fact, if you take this and multiply it by this, you get that. You can say, wait, you can't take two circuits and stick them next to each other and then do multiplication. Yes. So just like the transfer functions, you know the transfer function multiplies the input. This is so obvious, but here's your V in, and here's one circuit, and here's your V1, and here's your other circuit, and here's your V2, and this has transfer function 1 and transfer function 2. So V1 is equal to transfer function 1 times V in, and V2 is equal to transfer function V1. V1. V2 is equal to transfer function 2 times V1, so therefore V2 is equal to T1 times T2 times Vn. It's amazing that you can do that. You can just multiply things through. It doesn't always work, but it's such a clean way of thinking about things.